Okay, this section I'm now going to go through is the last section in the enthalpy or thermodynamics. We call this free energy, and we'd left it on the biting point where, or the cliff edge, where we had change in delta S or delta S, and we still had this issue where some negative delta S's still actually do happen. Okay, so so delta S that we left it with last time is not the full answer. So I'm going to share my screen and we'll get rid of that and we'll come on to here. So we're going to be looking at free energy. Okay, so apologise in the last video, I don't think the animations worked, but I think that will work in the way that I'm doing it now. Also, I've got quite a squeaky chair, you might hear that in the background as well. Okay, so what we're looking at, we're going to be looking at the free energy and link the entropy change with the enthalpy change of reaction, and it's going to be very dependent on temperature. Okay, we will come up with this new term called the free energy, delta G, which is much more reliable in ways of determining whether the reaction works, but also it allows us to get to this relationship, and it allows us to combine the surroundings with the system. Okay, because currently with S we've been looking at the change in the system, and even with enthalpy we're looking at the change to the energies in the systems. Okay, so hopefully you'll be able to calculate entropy and enthalpy changes and use the relationship that links the enthalpy change with the entropy change. Okay, and as we said, the sodium chloride dissolving, it dissolves, but it's endothermic. It's a +1 kilojoules per mole when we worked it out previously. There is another thing we can link it to. We can also link delta G to Gibbs to the equilibrium constant. Okay, so we're sort of tying things together. So the key words for this are on page 101 to 105 in the textbook. But we come up with Gibbs free energy. It's the free energy change. It's in essence, it's the energy that is available to be able to do work, really. Okay, it's a balance between the enthalpy, okay, which is the energy in the chemicals, the entropy, which is the ways of arranging that energy, and the temperature where things are happening. Okay, and now this is need to try not to get your knickers in a twist, but delta G needs to be less than 0. If it's smaller than 0, it's feasible. Okay, actually, if it's larger than G, it's not feasible. If it's 0, it's probably going to be at an equilibrium. Okay, so all these guys here, or these people here, were very famous in the development of our ideas of thermodynamics. Okay, so we had Maxwell, which we had before. He came up with the Maxwell distribution, and with Boltzmann and Maxwell were probably working probably independently, but they came together to get that Boltzmann-Maxwell distribution. The guy that we're looking at today is Willard Gibbs, and so the Gibbs free energy is named after him. And as I said before, these guys were, they're all great people, but they didn't, well, at least I think they were great people, but they didn't have a good way of describing what entropy was. And we now sort of talk about it in terms of the tendency of the energy to be dispersed, okay, and spread out. So, is the entropy change that we looked at before enough to decide a reaction will take place? Okay, so we said, so the entropy is linked, very definitely linked to the second law of thermodynamics. It states that entropy always tends to increase. In other words, to disperse, to spread out, go from solid to gas. Okay, is a good way of doing it. What if it doesn't? Do chemical reactions always go from ordered to disordered? What about precipitation reactions? You're going from aqueous solutions, which have an element of, let's say, disorder, although we don't really necessarily like the word disorder, but the solutions have got the energy more dispersed, to a solid, precipitate, which is a solid, and therefore the energy is less dispersed. Or you could potentially say that a precipitate is more ordered. So what have we not considered? We haven't considered what's happening in terms of the energy being transferred between the system and the surroundings. Okay, so if we have a closed system, okay, so this is a closed system, the reactants will become products. Okay, that is the system. The chemicals are the system. Okay, but energy will be transferred between the chemicals and everything that's surrounding them. So if you've got things happening inside a beaker with solutions, the water that surrounds all the substances, okay, that is acting as the surroundings. Yeah, it's in effect a closed system because, well, unless a gas is produced, because the solutions are staying there and anything else that's happening in there will stay in that solution, as I say, except if it turns into gas. Okay, or you could do a gas in a box or gas in a box. Okay, so we're transferring the energy between the chemicals, the substances, and the surroundings. Okay, so in an endothermic reaction, we're going to go from surrounding to the system. Okay, so endothermic reactions take heat energy in, so they're grabbing it from the surroundings and going into the system. And obviously in an exothermic reaction, it's the opposite. The chemicals are pushing it out into the surroundings. So what is the impact on the entropy of the surroundings? So we have to consider that as well. So in the previous ones, we've seen some reactions which have a negative entropy, which doesn't seem sensible. We might have two aqueous solutions turning into an aqueous solution and a solid, and a liquid that we saw earlier. That should that is a negative change in entropy. So that shouldn't really work unless we consider the surroundings. So we need to look at the change in the surroundings. If it's exothermic, the entropy of the surroundings is increasing. Okay, if the surroundings are if we've got an endothermic reaction, the entropy to the surroundings is going to be negative. So we need to take into account when working out if a reaction is feasible. Okay, so yeah, so let's go through that again. If a reaction is exothermic, the entropy increase of the reaction is positive. Okay, if it's an endothermic reaction, the entropy of the is negative. Okay, so this is the overall change in energy during a chemical reaction. It's made up of two types of energy. We've got the enthalpy delta H, okay, which is the energy transfer between the system and the surroundings. Okay, so if it's negative, which is exothermic, energy is leaving the chemicals and going to the surroundings. Okay, if it is positive, i.e. endothermic, the energy is being taken from the surroundings and going to the system. Okay, so the entropy change of the system, okay, is T delta S. Okay, so remember it's joules per Kelvin per mole. Okay, so if we increase the temperature, we're going to have more entropy. The change in entropy is going to increase. Yeah, so the entropy of the system, which is delta S, is going to increase. So it's a measure of how much the energy is dispersed within the chemical system. And eventually we can then say that delta G equals delta H minus T delta S. Now, you need to know that. You need to learn that. That's why it's in red. Make sure you know it. Okay. Okay, so you do not have to derive the equation, but for those of you who are mathematical, we're going to do it anyway, just so you can see how it works. So, second law of thermodynamics states that for a reaction to be feasible, the total entropy has to increase. So delta S total has to increase. Now that has to increase. It's got to be bigger than zero. However, we haven't got delta S total. Okay. From what we did last time, all we've got is delta S of the system. Okay. We've got the change in entropy of the chemicals, but we haven't got the change in entropy of the surroundings. So we can define total entropy change as the entropy change of the surroundings plus the entropy change of the system. Okay. So the entropy of the surrounding is affected by the enthalpy change of the reaction. So if we are having an exothermic reaction, it's pushing energy into the surroundings. Okay, so heat is transferred to the surroundings, hence there's increase in disorder. We're spreading the ways of arranging the energy more if we increase the heat. Okay, the relationship between the enthalpy change of reaction and the enthalpy change of the surrounding is given by this equation. So, so the surround, yeah. So basically, if you think about it like this, delta H is minus, it's exothermic. The chemicals have lost energy. What's happened to the surroundings? They've gained energy. So if it's exothermic, you've got minus times a minus. So the surroundings becomes positive and goes up. But it's affected by the temperature. Now let's think about this. Why is it divided by temperature? So let's let me just pop that in there. Let's put some numbers in there just so you can see how that works. So for instance, okay, say we've got the delta H, okay, is exothermic and equals minus 200. Okay. Now, if we have the delta S surrounding is minus minus, so we've got minus times minus 200. Okay. So the enthalpy of the surroundings has gone up to plus 200. Okay. So the enthalpy of the surroundings has gone up. The enthalpy of the chemicals has gone down. Chemicals have lost energy and the surroundings have gained it. So it's plus 200. Okay, now I'm just going to rub that out so we can continue. So let's eraser. Okay, so let's get rid of that. Okay. Okay. So that, we just want to go back to mathematics. So yeah, okay. So minus delta H, yeah, means that if we're exothermic, we're going to get a positive delta S. Yeah. Now, why does the temperature affect it, and why is it why does the temperature reduce the surroundings? Let's try and think of it this way. If I'm trying to push energy out into the surroundings, okay, I want the surroundings to be cold so that the energy will spread out, okay, and try and warm it up. Okay. However, if the surrounding is already hot, there's less places that this new energy that I'm giving out from the chemicals, there's less places for it to go. So temperature is going to affect the delta surrounding in a negative way or an inverse way. So this is why delta surroundings, okay, is minus delta H divided by temperature, because temperature, the hotter it is, the less the ways are of spreading out the energy. If you're putting more energy to something that's already hot, there's less places for it to go. If you're putting more energy into something that's cold, there is more space for it to go. So we can therefore rearrange it. Okay. Okay. We said that minus T delta S. Well, we're going to say that the minus T delta S total is equal to the Gibbs free energy change. Okay, so that makes sense because we've said that we want delta S to be positive, delta S total to be positive. If it's positive, okay, we want delta G ends up being negative. Okay, so that makes delta G negative. Okay, but we can therefore derive the further part of this equation. Okay, so we can pop this into there. So let's have a look. Let's see how that's derived. How do we get from that to that? Okay, so we've already said that delta S surroundings is minus delta H over T. Delta is system is what we worked out from the entropy of the components, which we did in the last lesson. Okay, we want delta S total. So delta S total's got to be this plus this. Okay, so let's see how we derive it. Okay, so if delta S is that, substituting in delta S surroundings for this, we then get that. So we replace this with this from that. Okay, that's okay. Multiplying everything by minus T, we get this. Minus T delta S total, okay, equals delta H reaction minus T delta S system. And we've already stated that we're now going to call this the free energy. Okay, the energy that is related to the temperature and the entropy. Yeah, so that's the free energy. So now we can just put that in. So that is how we've derived it. What you really need to be able to do, though, is make sure you can use this equation as it is. And we can get values for this, and we can get values for this. Therefore, we can work out this value. So free interchange, delta G, we want that to be negative. Okay, it determines whether it's feasible. If it's negative, the reaction is feasible. That doesn't mean it necessarily happens, just means it's highly feasible. If delta G is positive, reaction is not feasible, not going to happen. Okay, and if it's 0, it's going to be at equilibrium between in the products. So what signs and of delta H and delta S would give us a feasible reaction? So let's see what we can, well, let's put that into a nice graph. So we want this to be, right, so if delta H is negative and delta S is positive, a reaction will be always feasible as delta G will always be negative, okay? So if this is negative, okay, then, okay, and that's positive, yeah, you've got minus something. So you're not going to make it positive, yeah? So if this is minus and you take minus something here, it's going to be end up minus. You can't get away with it. It's got to be negative. So therefore, it's always going to be feasible. Okay. And so if delta H is negative and delta S is positive, it's always feasible. Yeah. So if we've got an increase in entropy in the chemicals, okay, so that delta S there is a delta S system. If we've got an increase in entropy in the chemicals and the enthalpy is negative as well, or exothermic, then the reaction is definitely feasible. Okay. If delta H is negative and S is negative, it's only going to be feasible if this negative is larger, or the magnitude of this negativeness is larger than the magnitude of this negative. Okay, so temperature has to be kept low. Yeah, so if this is negative, except it's exothermic, but the entropy is positive, is negative, entropy suggests it shouldn't happen. If this temperature is low enough, then this will still be negative overall. The whole thing will be negative. Okay. Now, if delta H is positive, okay, right, then we need to take away something, all right? So that means this has got to be positive still, because negative times a positive is still negative. Okay, so we want delta S to be positive. And therefore, what we need to do, because S is only small values in joules, not kilojoules, what really is likely to happen is if we increase the temperature, okay, i.e. endothermic reaction. So if this is an endothermic reaction, okay, if we increase the temperature, then that explains why endothermic reactions will happen as we increase the temperature. So remember when we talked about equilibrium to the Chatelier's principle. Okay, right. And finally, okay, a reaction will never be feasible if delta H is positive and delta S is negative. Okay, it's never going to be feasible if this is positive and this is negative, because if this is negative, negative times negative makes this positive. You've got a positive plus a positive. You're never going to get it to be negative. So in that case, the reaction is never feasible. So that's an endothermic reaction, okay, which will be positive. And it's if you look at the chemical and the entropy in the chemicals, the chemical entropy is negative going from reactant to product. Okay, so it'll be never feasible. So we can have a look at the units and see how those come together. So units delta H are kilojoules per mole, as we said, and I mentioned it earlier, in 22.4. The units for delta S are joules per Kelvin. So we need to make sure that we convert delta S into kilojoules per degree per Kelvin per mole. Okay, how would we do that? Well, we need to divide them by 1,000. Okay, so that delta S section of the equation up here is always, delta S is always going to be pretty small compared to the enthalpy. So what the units of T should be in Kelvin, not degrees Celsius, so it's got to be in Kelvin. Okay, any temperature in Celsius need to be converted to Kelvin. How do you do that? Yep, you have to add 273. Therefore, what are the units of delta G? Okay, well, they're going to be kilojoules per mole. Okay, because you've got kilojoules per mole minus kilojoules per mole per Kelvin. Well, that's per Kelvin on delta S. That is Kelvin. Kelvin times per Kelvin gives you no kelvins. So that also ends up being in kilojoules per mole. So therefore, the units of delta G are kilojoules per mole. So calculating it, here's an example. Right, we've got 4 copper oxides making 2Cu2O plus O2. Okay, so we could calculate delta H using the Hess's cyclone equation. So we could do it from formations. Okay, so the formations would give us that delta H is the sum of the formations, the products minus the sum of the reactants. So we can now find those. Now these are values that we would have, okay, given to you in a question. So we've got 2 lots of this, and its enthalpy apparently is minus 166. So 2 times that. Enthalpy of formation of an element in standard state is 0, so that's plus 0. And then we've got the formation of the 4 copper oxide. We have to take it away because it's a reactant. So 4 times minus 155.2. That gives us an overall enthalpy of plus 287.4. Oh dear, that suggests that the reaction shouldn't happen because it's endothermic. Let's see what happens if we do work out delta G eventually. So delta S, what do we need to know there? We need to know the entropies of copper oxide, copper 2 oxide, copper 1 oxide, and oxygen. Okay, so and to work out that, we would therefore need to know the entropy of the products, take away the entropy of the reactants to give us the entropy of the system. So apparently the values for this are, this is 100.8, so 2 times that. Oxygen is 204.9, so that should be added together. Take away the entropy of the reactants, 4 lots of 43.5, gives us an entropy, a change in entropy of the system of 232.5. Okay, so we need to get that into kilojoules per mole, so we need to divide by 1,000. That comes out as 0.235. Now we've got delta H and delta S. What do we need to calculate? Delta G. We need to pop it into the equation, but we also need the temperature. Standard conditions, 298 Kelvin. Sometimes you'll be told what the temperature is, and you'll have to take that into account. So now we can say delta G equals delta H minus T delta S, which is equal to 287.4 minus 298 brackets times 0.2325. Okay, so that comes out as 218.1 kilojoules per mole. Is that reaction feasible? No, it's not. Okay, so it's not feasible. Okay, because you know, this take away this ends up as a positive number. Okay, basically you got about a quarter. You end up with about a quarter of this. Okay, so it's 287 minus a quarter of 298-ish, which gives you that. Because 0.23 is about 25%. G23, obviously. Okay, so the importance of temperature. So as the temperature rises, so at the moment, that does not seem feasible. But potentially it could be feasible if this becomes larger, if the temperature becomes larger. So importance of temperature. As temperature rises, entropy becomes more important because, you know, the entropy is multiplied by the temperature. So if the temperature goes up, this whole term here, T delta S, becomes larger. So if delta H and delta S are both positive, there must be a temperature above which the reaction becomes feasible at high temperature. If delta S are both negative, there must be a temperature below which it becomes feasible. Okay, so you know, an endothermic reaction like the last one we just did will become feasible because delta S is positive. It will become feasible at a certain point, and an exothermic reaction does become feasible at a lower temperature. Okay, so it's that temperature where equilibrium is established. So we can actually work out what that temperature is, because I've already said that the value of delta G at equilibrium is 0. So calculating temperature when a reaction becomes feasible. So we had this one. We found out it was not feasible, but could we work out temperature when it is feasible? Delta G has to be 0. Delta H equals that. Therefore, if we've got delta G equals 0, then this is true, yeah, because delta H is also delta G is also delta H minus T delta S. If that's 0, then we can move that across the other side, and basically they're equal to each other. Okay, so we then trying to get temperature, so we need to do delta H divided by delta S. So in this case, we've got 287.4 divided by 0.2325. Okay, so if you divide by a small number, less than 1, you make the number bigger. So that makes sense. We've got 1236 Kelvin, or take away 273 and you get 363 degrees Celsius. So at this temperature, that last reaction would become feasible. Okay, so now it's time for you to have a go at working some out. Okay, so stop the video here, play on when you're ready. Okay, so summary. Okay, entropy is going to be larger if you've got a gas. It's going to be smaller if you've got a liquid, but it's even going to be even smaller if you've got a solid. Okay, the entropy of the system is going to be the sum of the entropy of the products minus the sum of the entropy of the reactants. Delta H is the sum of the formations of the products minus the sum of the formation of the reactants. Delta G is delta H minus T delta S. Okay, temperature should be in Kelvin in all these cases, so degrees C plus 273. We must remember to convert the delta S from joules to kilojoules. Do that by dividing by 100. If delta G is negative, okay, we get a spontaneous feasible reaction. These other equations may also be useful. So if instead we don't have the formation data for our products and reactants, we might have the combustion data. If you're working out delta H of a reaction from combustion, it's delta HC of the reactants minus delta HC of the products. So the other way around to delta H formation. Also, you got the same equation if you're breaking bonds. So if you've got bond energies of the products and reactants. So it's the bond breaking minus bond making. So it's the bond's energy of the reactants minus the bond energy of the products, or bond enthalpies. So here's a summary of feasibility. Okay, the temperature at which the reaction becomes feasible is when T equals delta H over delta S, because delta G has to be 0 at equilibrium, and at that point you're at the cusp of a feasible reaction. So this table summarizes that. Okay, if delta H equals minus or is negative, i.e. exothermic, and delta S is positive, then the reaction is always going to be feasible. Delta G will always be negative. So delta G being negative means the reaction is always feasible. If delta H is positive and delta S is negative, okay, then delta G is positive, the forward reaction is not feasible, but the reverse reaction would be feasible. Okay, so that, that's something to bear in mind, that the reverse reaction would be feasible, the forward one is not. If they are both negative, then temperature must be low in order for the reaction to be feasible. If they're both positive, then temperature must be high to make it feasible, and hopefully you can read the scales on that to see that. Okay, so I'll leave that for a second more. Okay, that's a very useful table. So thermodynamics and KC. So we're nearly at the end now. KC is related to delta G by this relationship. And in that relationship, we know what R is. I hope you know what R is. You can stop and think. Okay, R is the ideal gas constant. Okay, and it's 8.31 or 8.314. It's on the data sheet. Ln is the natural log. Okay, so the natural log of Kc. Okay, and what does a large value of Kc mean? So if Kc is large, that means you're favoring the products. Okay, so you get a good yield. So as Kc gets larger, what's going to happen to delta G? As this bit gets larger, think what's going to happen to all of this overall. This bit here is going to become bigger, and so delta G becomes more negative. Okay, and therefore more feasible, which makes sense because we've said that it's favoring the products. Okay, so that's the link with Kc. Okay, and that is it for this session. Okay, so obviously you can stop the video now and have a look at and go through these questions. And this is what we've covered. Okay, so the red stuff is the easier stuff, orange is more tricky, and green is the sort of what you need to be able to do. Okay, so I think that is it, and also understand that delta G is minus RT log Kc, and hopefully you can see how if Kc is large, we're favouring the products, which also means reaction is more feasible because of this linkage here. So let's finish with that, leave that up there. Okay, leave the task list up here for you to work through. There we go. Some of this obviously extension stuff on Moodle. That is the end of the thermodynamics section. So you really ought to have a go at finishing all the questions in the chapter at the end of chapter 22. Thank you for watching, if you have been. Let's see if I can get into the video. And I can now stop.